Forget frequently asked questions.
Common sense, common knowledge, or Google.
How about advice from a real genius? 95% of people in any profession are good enough to be qualified and licensed. 5%
go above and beyond.
They become very good at what they do, but only
0.1%
are real geniuses. Richard Jacobs has made it his life's mission to find them for you. He hunts down and interviews geniuses in every field: sleep science, cancer, stem cells, ketogenic diets, and more. Here come the geniuses. This is the Finding Genius Podcast
with Richard Jacobs.
So this is Richard Jacobs with the Finding Genius Podcast. My guest today is Blair Lock. He's the CEO and co-founder of Coapt medical devices. And these devices apparently work with prosthetics to allow the prosthetics to be controlled from your nerves, which is really interesting. It's like a next gen in prosthesis control. So we'll go into the details of that. And Blair, thanks for coming.
No problem. Thanks, Richard, for having me.
Yeah, why the interest in prostheses? Do you need one or use one, or what's your background?
Yeah, I don't personally. It's an incredibly niche field, and if you've ever had the pleasure of talking to others involved in this field, I'm sure you found it's a passionate group of people. It's a very interesting space that is rewarding in a way, because you're being able to give back or sort of add to somebody in the need of a prosthetic device and who relies on these devices on a daily basis in their daily function.
Well, I think the prosthetic world is divided into upper limb and lower limb for some reason. I don't know if that's right, but what kind of prosthetics do you focus on?
Yeah, the types of prosthetics that we'll be talking about are loosely divided: upper extremity, lower limb, upper limb. Yes, there are other prosthetic devices out there, eyes, ears, nose, for example. But as far as prosthetic limbs, we do consider ourselves the same field, along with the professional orthotics discipline. But specifically what Coapt does, and where my background and interests have been, is in the control of upper limb powered prosthetic devices. Now, these are what we can see. Sometimes we see them in popular media or other uses, where you have a bionic looking robotic like upper limb prosthetic device. It's very difficult for sometimes to explain where Coapt's niche in that world is. We don't necessarily make anything you see. So the hands themselves, these very robotic hands, the joints that move, the wrists, the elbows, for example, we only make the control system. And it's a very special control system that's a finely tuned neurological decoder, in a sense, that can take information from the biopotentials, the signals of the human body, the human wearer, and convert those into control commands in real time for those robotic hands and other robotic joints to respond and become a functioning prosthetic device.
So people can literally, do they have to look at the prosthetic? They can will their arm or their hand to move in the way they want, or do they have to look at the device? What did it look like when this first came about, and what does it look like now?
Yeah, so the function, it can be thought of, and it's often described in a few different ways, but the neurological decoding aspect, effectively, any human, when we make muscle contractions, just in general, any muscles that contracting muscles, it really emit a small amount of electrical activity, electrical noise. Think of it like music that we can't hear at a very, very low electrical level. Now, at any movement of a hand or wrist or an elbow, we have a number of muscles that are contracting together in a small concert. And therefore, they're sort of emitting this concert of noise, this concert of information. Neurologically, that's a representation of the signals that are coming from the brain, out the nervous system, and being amplified by these muscle contractions. What we do is we can detect these small electrical signals, this concert of activity, and teach algorithms. So in the machine learning aspect, learns the music, the personalized music of each wearer, of what that means. So for example, anytime somebody is opening a hand or imagining opening a hand, their nerves are telling the residual muscles, so they're muscles that remain in an amputee, to attempt to open that non-existent hand. The muscles create the pattern of activity. Our system can detect that, know what it is from previously training the decoder, and therefore command the robotic device to open. And this all happens in real time. So some will say, yes, you're thinking about it, but effectively you're still making muscle contractions for those parts of your limb that are no longer really biological.
Well, I feel like I don't think about some of the things I do. The motion just happens. And I'm imagining when you first interact with a prosthetic, you probably have to maybe look at it and think about moving. Maybe there's a lag and then it moves. And over time, are you able to train it so that you don't think and it just moves and it matches what you do with your normal hand or leg, or does it never get to that point?
It can become very intuitive for the people who wear it. Yeah, so in the beginning, there is a bit of a learning process. There's becoming one with this system. Both it learns the signals of the user, the wearer, as it's being worn, so more and more, and also the individual wearing these devices tends to get better at the tool. A good prosthetic device is a really effective tool for these wearers. We are not in the place in our engineering capacity to be able to replicate how amazing the actual human limb is. So it is a tool, and we provide the system that just makes sure that the tool is controlled as intuitively as possible. True thought control is a little bit different. The most kind of common thought about this, or the research area, is if you were to have detection of thoughts, so from brainwave activity, for example. Now, there is research. There has been lots of research in and around the prosthetic space about that, so about thought-controlled devices. While that's very powerful, the research is very compelling. On a practical day-to-day use standpoint, we're not quite at the place where that is a sort of practical use rollout. So where we're providing this peripheral neurological connection that requires your thought in using the tool, it still is a very intuitive mechanism of controlling a prosthetic arm.
Yeah, I just feel like I move certain things without thinking about them. I guess I don't know, I'm thinking on some level, but other things are deliberate thought, but it may be just for a moment. So
that's right.
What's the interaction like? I mean, what has the interaction been like in the past? What's it like now with your tool? How's it different?
Yeah, so it is helpful to understand kind of the past style of control. So myoelectric, what we would call myoelectric, that's the electrical activity coming from muscle, myo. Myoelectric prosthetic devices had traditionally been controlled in a cumbersome manner. They did use electrodes, and typically on the example of a below elbow amputee, there would have been one, maybe two electrodes. And these two electrodes would be placed on what we call an antagonistic pair of muscles. So one electrode on the area of muscles kind of on the inside of your forearm, where if you were to flex your wrist in, you can kind of feel the inside of your forearm tense up. And if you were to extend your wrist out, you feel kind of the opposite side, the outside of your forearm tense up. Well, if you put one electrode in each one of those areas, you get a very back and forth A versus B antagonistic two input system. And those two input systems were what was used. Now, the signals are generalizable to most people who are wearing that, but the activity, now I'm asking somebody wearing this to imagine flexing and extending their non-existent wrist in order to do a hand function, perhaps a rotation. So perhaps something that's kind of a one-off. It's not intuitive. People can use that, but it's limited in that cumbersome nature. And now, in this day and age where we have much better prosthetic devices, so what we would call multifunction hands that do different grip postures, it's hard to imagine two very low bandwidth signals controlling all of that. So we got into a scheme of trickery, a series of pulses, kind of Morse code like, to trigger different functions of the prosthetic limb. Fast forward to what Coapt does in not just taking very basic information from two sites, but the high fidelity information from a collection of sites. You start to get at the information of these muscles, hence the neurological content, not just the loudness. You're not comparing the loudness of muscle section A versus muscle section B. You're getting that content. And with the machine learning techniques, you teach the microcontroller with all of that fidelity in order to directly command, say, I want to point with the prosthetic hand or make an OK sign or rotate the wrist around, for example. So it's very fast, very intuitive. And when it comes to thinking about it, yeah, it is a little bit different. It takes a little bit of practice. Now, you and I, we don't often really consciously think about the muscles we're using if we go to, say, grasp a cup of coffee. However, when we do that, if you are aware of, I want to feel what my muscles feel like when I'm making a peace sign or a thumbs up sign, you can kind of feel what that's like. You're aware of kind of closer to your elbow what those different muscle tense feelings are feeling like. And that feeling is effectively what somebody using this technology is imagining.
So I guess you have to train yourself and deliberately work on some actions and learn how to engage your muscles in what order, with what intensity, etc. Probably a range of actions, and then you begin training yourself on them to interact with the prosthetic. Right?
Yeah, training is a interesting concept. There's a number of things that get trained in a classic machine learning or engineering speak. We often talk about training the algorithms, which is true. But in a real world human prosthetic speak, training is also important, where we have a user, once they learn the control system, once they understand the mechanism of control, the training should and does turn into occupational therapy, where I'm now using that tool, that prosthetic device that I'm controlling intuitively, in training myself how to incorporate my daily life, how to manipulate objects, how to do two-handed items, how to make that prosthetic device be part of my day. On the algorithm side, what's fun about that is teaching the device. We let the user teach the device what is intuitive to them. So the very initial and continued learning process of the algorithms is where we, the user goes through a sequence where the prosthetic device will go on its own motions. So it will, if there's a motor that rotates the wrist, for example, it will do that. If there's different postures of the hand, it will cycle through those. And as it's doing that, we ask the user just to follow along. They play Simon Says. They're mimicking those motions with whatever musculature, with whatever feeling they have. So in that sense, we let them teach the prosthetic controller what exactly is intuitive to them, versus saying, hey, you have to do it this way in order for the prosthetic to respond. We flip that a little bit, and we let them teach the prosthetic device what their personal signals look like.
Are people able to only do a fixed set of actions? And what happens if they try an action that they haven't specifically trained on? Will the prosthetic not work or not function properly, or what will happen?
Sure. So the set of actions available to them is always defined by what prosthetic components they're wearing. The Coapt system has been designed to be fit. It's kind of an add-on controller kit to be fit with all of the commercially available hands, wrists, elbows that are on the market. Each one of those has its own characteristics. So some hands do more functions than others. So if a wearer chooses one hand that has 5 functions, well, then those 5 functions will be available to them. If another hand maybe only has 3, well, those 3 functions are available to them. And what happens in the sense where the wearer does something that sort of something with their neurological signals that isn't one of those functions, the system is also trained to recognize, for the need of robustness, to recognize when they're not doing something specific, not one of the prescribed motions, that it won't turn or it won't move the prosthesis on its own. And that's very important for function. It's as important for this device to behave when you don't want it to go into a hand posture or move the wrist or move the elbow, for example. So it's quite good at recognizing when it shouldn't move.
So you can't do motions that you haven't specifically contemplated or that the device won't let you do, or what happens?
That's right. Mechanically, the limitation is really mechanics at this point. Most of the commercially available prosthetic hand devices are, they can be actuated in predefined grasp postures. So a lot of people, a misconception is, hey, is this individual digit control? Is somebody free to make digit commands with what is coming out of the control system? And not really, not at this time. And that limitation is because of the way the commercially available hands are controlled.
So is that a desire? I mean, that seems like it would be I guess you get some initial freedom and you could do a few things, but then, you still can't really have the hand do whatever you want to do with it. The problem seems to be very limiting.
Yeah, it is. It's definitely not limiting. I think it's a huge step over what the incumbent approach has been. The desire is there. Fundamentally, what's really gone on in our space, you'll see a bit of a development history of leapfrog. So the devices themselves, so the mechanical hands, for example, progressed to a certain level where they outpaced the ability to control them very well. And now, with the advent of the Coapt system, we've kind of taken the step beyond what the restrictions of the mechanical devices are. So for the next little bit, I think we'll start to see some of our research, for example, starts to bring those back together. So in order to make it even more intuitive and more flexible and more sort of natural all the time for the users, there has to be continued co-development with the devices and the control systems together.
Since you're looking at, I guess, impulses generated from someone's muscles, if I lost my left hand, do I have to train using my right hand because I have all the muscles there and learn what to do first and then say, all right, I'm going to recreate this in my mind for my left hand, which is missing in order to do that action? Or can you just do it by having intent and pretending to move muscles that may not be there?
If I understand that correctly, so sort of left to right, if we could say our amputated limb, it's reading signals from electrodes that are within the socket on that limb. So nothing really comes from the contralateral side. We don't have to kind of co-active. There does need to be musculature in there for this type of electrode to work. Future work, there is good research, including some of our own research on really getting into nervous system signals at a lower level to get around the need of actually having a lot or strong muscle signals. That's a little ways out just from the technology. And one reason that is, people often ask, why is that? There's really a few ways to get information from the nerves themselves. The challenge is the nerve signal is many, many, many times smaller in an electrical sense than the muscle signal itself. And the muscle signal is already 1,000 times smaller than just the electrical activity on our body because of the lights and wires in our walls. So the muscle information is already difficult to record from the skin surface. The nerve signal is really harder. Ways to get through this, we'll see kind of muscle signal decoding to break down the noise or this music that comes from any muscle into its fundamental components, which in there are representations of the nerve signal. And so that takes a lot of processing and some hardware that is under development and some great promise there. The current commercially available prosthetic devices and the commercially available prosthetic controllers are not at that level yet, although they are really quite advanced.
So this is more for someone that, their arm is paralyzed but not amputated.
Nope, this is for amputees only.
Okay.
Again, if we imagine, let's imagine somebody who's suffered a loss of their arm from about mid forearm down. Most of the muscle that's between your mid forearm and your elbow, so in that sort of top half, contains a lot, if not all of the muscle information we need to command all of the hand and wrist functions of the commercially available prosthetic devices.
But if I'm missing my hand, what about the muscles of my fingers? That's why I was wondering.
Yeah. So physiologically,
if you could train me on, let's say I still have my right hand and I have the muscles of my fingers. If I move them, could you train the system so that it knows, okay, when I move my fingers, my right hand, they tend to do this, that, and the other and make these signals. So then maybe the system then could allow me to move the fingers on the robot hand on the left arm, because now it's similar, it's just a different hand.
Yeah, well, we get actually kind of a lucky thing physiologically. If you really think about it, there's not that many muscles in our hand. A lot of our hand and wrist motions are controlled by those muscles closer to the elbow, and they pull on the tendons that go through the carpal tunnel. So in a bit of a lucky sense, all of that information physiologically, even though I perhaps have suffered amputation mid forearm, that information that controls the motion of my hand is actually happening closer to my elbow. So what happens there is we put electrodes on those muscles, those remaining residual muscles, and they're representative of all of the activity of my hand and wrist, for example. So in some sense, we have a benefit of what the natural physiology of the human body is.
Do you think there's anything to be learned from someone that still has the other limb?
Yeah, we do that a
What's
lot.
unique to them?
Yep. So sometimes that's helpful in training. It just helps sort of in the neuroplasticity side, get somebody kind of used to the way of thinking about controlling their muscles. But we also, in development, we do this a lot. We have a lot of systems where we can kind of strap on a temporary like system to ourselves, or our engineers, our teammates can use this to develop. So you or I can put on an evaluation system that we have and control a virtual prosthetic arm on screen, for example. And that's quite straightforward. We've been doing that for decades.
What's that like versus actually having a hand, a prosthetic hand?
Hard to say. I've not had a prosthetic hand. I think the users who can use a prosthetic on, say, the left side and try it out in an evaluation sense on the right side do find it very relatable.
Interesting. So what's the path forward then? I mean, from here, you're able to, again, read the muscle contractions. You said it's lucky that, if someone, again, is missing a hand, that a lot of the musculature is still in the forearm. But what's the next path? And is the next path now to read the nerves and then maybe even thought later on, or just become more sophisticated and have a bigger range of motions for an amputated hand? What could you do?
Yeah, maybe. There are a number of different directions that the research is taking collectively. And there's a large community of people worldwide, studying and researching and developing in this space. And I think kind of all of the above. We have that luxury for a below elbow amputee, but even an amputee who is above elbow or lost their arm, say at the shoulder level, there are some surgical techniques, one called targeted muscle reinnervation, which really helps remap some of the physiological nervous system to help us get these control signals out. That's a great advent and a great area of future work. Other things like further decoding muscle signals to get at the nerve content, moving more centrally, or what we would say is reading that thought about something that's inside the brain. Another kind of hot area of development that we and others are involved in are sort of subcutaneous sensors. So you can imagine kind of implanted electrodes under the skin, or even electrodes or sensors that can read information from the nerves in a peripheral standpoint. That gives us even higher fidelity of access to information for control of the devices. Talking or hearing from the muscle signals from under the skin is just like having a conversation in the same room as somebody versus trying to have that conversation through a wall. And in our metaphor, the wall is the surface of the skin. We can do it. The electronics have to be incredibly sensitive and incredibly good to do that in a good way. So there are a lot of areas of development, but fundamentally, where we are with algorithms and the training and the machine learning and the AI applications to this type of data is very good. So I think just going forward, making sure the devices, so the mechanically actuated devices in the control systems and our decoding ability just continue kind of to progress in concert.
So what's the timeline over the next year? What do you think is going to be possible? And then maybe 5 years?
Yeah, it's generally in our space. It's the development is very careful. These are medical devices, so what we sell is an FDA Class 2 cleared medical device. While the developments can happen on a 6 month to 1 year standpoint, some of the reality to get to the commercial market can take a little bit longer. I certainly hope to see in the next year or so some more functionality with some of the powered prosthetic devices on the market. So it lets us expose some of the additional capabilities of our control system, for example. We're starting to see some of the sensory feedback. So devices are becoming smarter and able to sense the environment and provide that back in a meaningful way to the wearer. Are they touching something extra? How hard are they grasping an object, for example? So there are a lot of areas in prosthetic device control that are kind of co-developing. It's realistically between the next 3 to 5 years is where I think we'll see the next significant jump.
So do you think it's ever going to be possible to, be like the movies where a prosthetic hand just can do everything? And the person thinks about it and it moves any way they want.
I don't know, but I certainly know there are a lot of people drawn to work in this field. Students, engineers, everybody that gets involved. That certainly has that out there as a target to make this as lifelike and as functional as possible. I think what's been great is that the professionals in the field are able to remove themselves a little bit from the sci-fi aspect and understand that what we're really after here is human function, helping somebody who's wearing a prosthetic device just make sure it's functional. This needs to be a beneficial, functional tool for them to wear. At the end of the day, they can be take quite a bit of their time and effort to be fit with these by a medical professional. Some of them have significant costs associated. So there's a great field out there just pushing the envelope all the time. Can we ever get to fully replicating the function and ease of use of a human arm? Boy, I don't know. I don't know that we'll ever see that in our lifetime, but certainly a target and a goal we'll all work toward.
Well, very good. Well, Blair, what's the best way for people to find out more about Coapt?
Yeah, I guess this day and age online is great. So coaptengineering.com. Coapt Engineering is one word. We are a Chicago-based company, and that's a great spot to start. There's some contact us or some basic information. There's some information for our product users. If there are prosthesis wearers, amputees who have a powered prosthetic device and are interested in this, we always encourage them to open the discussion with their prosthetist. So they are typically being seen by a medical professional, helping them fit and be functional in a prosthetic arm. And we'd certainly love to chat with all those people and educate wherever we can. The product itself has been available all over the U.S. for almost 8 years now, and as of last year, been in some select international markets as well. So we have a full team, happy to answer any questions, and that's a great place to get a start on from us.
Okay, well, very good. Well, Blair, the stuff you're doing is it's important to help people. I didn't realize it's so complicated. It's amazing,
Well, I appreciate that.
What biology can do, and it's hard to emulate. Yeah, thank you for coming.
I appreciate that. Thank you for having me.
You've been listening to the Finding Genius podcast with Richard Jacobs. If you like what you hear, be sure to review and subscribe to the Finding Genius podcast on iTunes or wherever you listen to podcasts. And want to be smarter than everybody else? Become a premium member at findinggeniuspodcast.com. This podcast is for information only. No advice of any kind is being given. Any action you take or don't take as a result of listening is your sole responsibility. Consult professionals when advice is needed.